Hi everyone, my name is Dr. N. Satish Kumar, working as Assistant Professor in the Department of Chemistry, Siddhartha Institute of Science and Technology, Puttur. Today, I am going to give lecture on one of the important bonding models in chemistry, that is molecular orbital theory. In our universe, there are so many elements is present. Except hydrogen, all the elements are composed of three important fundamental particles like electron, proton and neutrons. A bonding model like molecular orbital theory or valence part theory is useful to explain bonding between the atoms and their geometry and properties of the molecules. The molecular orbital theory was proposed by the two scientists Hund and Mulliken in the year 1932 to describe the structure and properties of the different molecules, and it is a very important theory to explain the electronic structure of the molecules. Electronic structure nothing but where the electrons are residing in a molecule. In the case of atoms, it is quite forward that the atoms have the electrons around the nucleus that are revolving around the nucleus. But in the case of molecules, whenever atoms combine to form molecule, we should know about the where the electrons are residing. So the molecular orbital theory gives picture about where the electrons are residing in a molecules, and this theory uses the quantum mechanics to explain the electronic structure of the molecules. And this is very successful theory because of failure of the valence bond theory to explain about the double triple bond nature of the molecules. Important postulates of the molecular orbital theory are: they assumed that when two atomic orbitals overlap, they lose their identity and form a new orbital called molecular orbital. Whenever atoms wants to make a molecule, the atomic orbitals are involved in the making of molecular orbital. So atomic orbital nothing but they are present in the atoms where the electrons are residing. So whenever atoms wants to form a molecule, their atomic orbitals overlaps and forms a new orbital called molecular orbital. In the case of molecular orbitals, they are useful to fill the electrons that is coming from the atoms. And there are some important criteria to make a molecular orbital from atomic orbital. All the atomic orbital cannot combine to form a molecular orbital. Those atomic orbital having comparable energy and proper orientation can only make into a molecular orbital. For example, if you take 1s orbital of one atom, the same 1s orbital of the another atom can combine to form molecular orbital, but not 1s orbitals of the one atom with the 2s orbitals of the another atom, because of the energy gap between 1s and 2 is quite high. So whenever atomic orbitals combine to form a molecular orbital, they should have not the same energy, comparable energies and proper orientation also. And the number of molecular orbital formed is equals to number of atomic orbitals combined. So if you take n number of atomic orbitals, they results into n number of molecular orbitals. Let's say precisely, if you take two atomic orbitals, they can produce two molecular orbitals. So for example, when we take two atomic orbitals to form a two molecular orbitals, one orbital is called bonding molecular orbital, another one is called anti-bonding molecular orbital. So bonding molecular orbital is formed by the addition wave function of the two atomic orbitals involved. So they have lower energy than the atomic orbitals are involved. In the case of anti-bonding orbitals, they are formed by the subtraction of the two wave function of the atomic orbitals involved, and they have higher energy than the atomic orbitals involved. And usually the bonding molecular orbitals are represented with sigma, pi, delta, etc., whereas anti-bonding molecular orbitals are represented with sigma star, pi star, delta star, etc. After construction of molecular orbitals using atomic orbitals, we have to fill the electrons in molecular orbitals using some formulas or rules. The filling of electrons in molecular orbitals take place according to three fundamental rules: Hobbe principle, Pauli exclusion principle, and Hund's rule, which are useful to fill the electrons in atomic orbitals. Hobbe principle tells that the lowest energy orbital filled first. In the case of Pauli exclusion principle tells that no more two electrons will have the same four quantum numbers. The Hund's rule tells us whenever there is a degenerate levels in orbitals, all the electrons should be the orbital should be filled with the electrons. Then only we can pair up the electrons. And atomic orbitals are monocentric, whereas molecular orbitals are polycentric. So atomic orbital have the electron charge only on certain atom, but whenever atomic orbital combined to form molecular orbital, the charge is distributed over all the molecule. And one of the important feature of the molecular orbital theory is to calculate the bond order. The bond order is defined as the number of covalent bonds between two atoms is called bond order. We can calculate the bond order using simple mathematical formula, that is bond order equals to number of electrons in bonding orbitals minus number of electrons in anti-bonding orbitals divided by 2. And one of the striking feature of the molecular orbital theory, we can predict the magnetic properties of the molecules also. For example, whenever molecule consists of the only paired electron, it is diamagnetic in nature. On the other hand, if the molecule consists of the unpaired electron, it is paramagnetic in nature. So we can easily calculate magnetic properties of the molecules also using molecular. There are two types of energy level arrangement of the molecular orbitals. Whenever a molecule consists of the more than 14 electrons, the arrangement of p orbitals are symmetrical in nature. Whenever a molecule consists of the less than or equals to 14 electrons, the arrangement of the molecular orbitals are unsymmetrical in nature. So this theory, the energy level is for the molecule having the greater than 14 electron, which is symmetrical arrangement. So in this arrangement, we will get the 1s orbital at lowest level after that antibonding 1s, 2s orbital after that antibonding 2s, and 2px orbital, sigma orbital. After that we will get pi 2py 2px, which are degenerate orbital have the same energy. After that we will get the pi star 2py and 2pz orbital, and finally higher energy level of 2px orbital. In the case of symmetrical and unsymmetrical arrangement, always the sigma star 2px orbital have the higher energy. It is symmetrical arrangement, that means whenever we put the plane between the bonding and anti-bonding orbital, the right side we will get the pi orbital, as well as left side also you will get the pi orbital. That is nothing but symmetrical arrangement of the p orbitals. Whenever a molecule consists of the less than 14 electrons or equals to 14 electrons, we will get the unsymmetrical arrangement. In the case of s orbital, sigma orbitals, the same energy will follow, levels will follow. First, 1s lowest energy level orbital, antibonding 1s, 2s, antibonding 2s, but here the pi orbitals like 2py, 2pz orbital have the lowest energy than the sigma 2px orbitals. After that, sigma star 2py, 2pz degenerate orbital, and finally always higher energy sigma star 2px orbital. Here, if you put the plane between the bonding and anti-bonding orbital, in the right side, the anti-bonding orbitals are pi orbitals, but the bonding orbitals are the sigma orbitals. That is nothing but unsymmetrical arrangement. This type of arrangement is follows by the molecules which having the electrons of 14 or less than 14 electrons. This type of symmetrical arrangement are followed by the molecules which having the electrons greater than 14 in their structure. And whenever any molecule have the bond order positive, the molecule will be stable. If it will get the negative or zero bond order, the molecule is unstable in nature. We can construct the molecular orbital energy diagram for simple homo and hetero diatomic molecules using molecular orbital theory. Let's say the best example is nitrogen molecule. The nitrogen molecule is composed of the two nitrogen elements. So whenever the two nitrogen elements combine, it can form the nitrogen molecule. So if you see the electronic configuration, the nitrogen have the electronic configuration of 1s2, 2s2, 2p3. Another nitrogen have the same electronic configuration 1s2, 2s2 and 2p3. According to molecular orbital theory, the atomic orbitals of the elements can combine to form molecular orbital. So here 1s orbital of one nitrogen element can combine with the 1s orbital with another nitrogen element to form the molecular orbital. Because of these two 1s orbital have the same energy, so they can combine to form two molecular orbitals. According to molecular orbitals, whenever two atomic orbitals combine, it can forms the two molecular orbitals. One is bonding a molecular orbital, which having the lower energy than the atomic orbitals involved. Another one is the anti-bonding orbital, which having the higher energy than the atomic orbitals involved. Likewise, the 2s orbitals of the two nitrogen elements combine to form two molecular orbitals: bonding orbital, anti-bonding orbital. Bonding orbital have the lower energy, anti-bonding orbital have the higher energy. In the case of p orbital can split into two sets of suborbitals. One is sigma 2p orbital, pi 2p orbitals. So already I told that the sigma star 2p orbital have the always higher energy than the all the p orbitals. So the nitrogen, if you count the total number of electrons, nitrogen one single nitrogen have the 7 electrons, the two nitrogen have the 14 electrons, so it should follow the unsymmetrical arrangement. So always we have the sigma star orbital in higher energy, after that pi star orbital. So we can consider when you put the plane, if you put the sigma orbital, you will get the unsymmetrical arrangement. Because of the top you will get pi orbital, the bottom you will get sigma orbital, which is nothing but unsymmetrical arrangement. The total number of electrons is 14, so we should follow this type of unsymmetrical arrangement. This is the construction of molecular orbital. After that we have to fill the electrons using the three fundamental formulas: Hobsbawm, Pauli, as well as Kunz rule. So 1s orbital, one element of nitrogen have the two electrons, total 4 electrons. We can start with the sigma orbitals, lowest energy orbital according to Hobsbawm principle: first electron, second electron, third, fourth. Likewise, 2s electrons. So we can fill the four 2s electrons in bonding and anti-bonding orbitals. In the case of 2p orbitals, there is total number of 6 orbital electrons is present. So we can fill the lowest energy orbital according to Hobsbawm: first electron, second electron, third, fourth, and fifth and sixth electron. In the case of nitrogen, the anti-bonding orbitals are empty in nature. We can calculate the bond order also. The bond order nothing but number of electrons in bonding orbitals minus number of electrons in anti-bonding orbitals. So 2, 4, 6, 8, 10. 10 electrons present in the bonding molecular orbitals minus 2, 4. So 10 minus 4, 6 divided by 2. So bond order is 3. Most of the case nitrogen forms the triple bond in nature.